The UDP checksum is the first end-to-end transport layer checksum we have encountered, meaning UDP is the first true transport protocol in the book that verifies data from sender to receiver, not hop by hop. So that's the first thing that we need to understand. How it relates to our previous messages, IP only protect its header, not the payload. UDP needs to verify your data because IP won't. Quick runs on UDP, so Quick relies on UDP's best effort behavior and adds its own checks. Second, it covers the UDP header, the UDP data, and a pseudo header, meaning when a UDP computes a checksum, it includes UDP header, ports, length, checksum. So the ports and length are actually in the checksum, and the source and destination IP address. UDP payload, your application data, a virtual pseudo header from IP, source IP, destination IP, protocol number. So this is how you change port number for your OS. Why? To ensure the datagram wasn't misdelivered, the destination IP or port was correct. How it relates to our previous message? You ask how a machine knows which datagram for TCP versus UDP. The pseudo header includes the protocol number. So this pseudo header is the one responsible for determining if the datagram is TCP or UDP. You ask how a sender or server knows which port to give the data to. UDP checksum includes the port. So not just the protocol but also the port, which helps catch mismatches. Third, it is computed at the initial sender and checked at the final destination, meaning only the two endpoints participate. Sender computes checksum, receiver verifies it. No in between, just like a TTL hop in IPv4. Routers don't touch it. Ties to our previous message, you ask how are UDP ports independent? Because routers don't interpret UDP, only endpoints do. Quick inherits this. It trusts UDP only for delivery, not integrity. So as you go up to the upper layer, such as Quick in user space, they don't care, or those layer doesn't really understand the lower layer or the upper layer. That's why the router just passed that UDP, and the UDP just passed that to Quick. Fourth, it is not modified in transit except when it passes through a NOT, meaning normally routers forward UDP and touch. NOT changes source IP and source port, so UDP checksum must be updated too. Relates, you ask how Quick solves NOT problems, because Quick's connection ID avoids relying on NOT stable ports. You ask how NOT rewrites ports. Here is the reason checksum must change too. So because NOT sometimes rewrite ports, remember, not just the IP. So the checksum must also be recalculated based on that to maintain that server to receiver integrity. Fifth, recall that the checksum in IPv4 covers only the header and is recomputed at each hop. Meaning IPv4 projects only the header. Meaning IPv4 protects only the header, not the payload of the IP. Unlike the UDP pseudo header, which actually protects both the UDP payload and the UDP header. Because TTL changes every hop, must recalculate, so only the header is recomputed as a checksum. IPv4 does not ensure payload integrity. Relation to mass message. This is why UDP or TCP must check payload. Quick over UDP adds even stronger cryptographic protection. So UDP actually adds integrity or checksum by checking the data, the pseudo header, and the UDP header. And remember, the pseudo header has the IP layer, so it will check the payload, entire payload of that as well if it's corrupted. And in user space, we have quick over UDP, which even um, add more cryptographic protection. So add more encryption. With UDP, the checksum is optional. With IPv6, it is mandatory because IPv6 has no header checksum. Meaning IPv4, UDP checksum equal optional. IPv6 UDP checksum equal required. No IP checksum to fall back on. Relates to, you ask why browsers and modern systems always enable checksums. Because RFC 112 mandates it. Quick uses UDP over IPv6 often, must compute it. To provide error-free data to applications, a transport layer protocol must compute a checksum, meaning UDP must verify that data wasn't corrupted. Relates, you ask why UDP is unreliable, not because of checksum, but because it has no retransmission. So when the packets get lost, it can be redo. So it ensures integrity of the payload, but it doesn't ensures it doesn't prepare for packet loss. Relates, you ask why UDP is unreliable, not because of checksum, but because it has no retransmission, congestion control, ordering. That's why Quick uses UDP but implements its own reliability layer. Technical detail section, broken down. UDP datagrams can be add number of bytes. Checksum requires even virtual pad bytes used. So a checksum requires actually an even. So a virtual pad, kind of like the padded we are being discussed before, to make it to make the hardware properly execute or compute it efficiently. Meaning internet checksum works on 16-bit words. If payload is add length, it add a 0 byte virtually. It relates. This is why you see UDP 1024 and TCP dump. Lengths matter to avoid fragmentation. Quick datagrams to stay below 200 bytes to prevent fragmentation issues. UDP computes checksum over pseudo header, includes IP addresses and protocol number. Meaning pseudo header is invisible but included in checksum, ensures the datagram arrive at IP plus port. It relates. You ask, how does IP demultiplex between TCP and UDP? Because pseudo header includes protocol UDP equals 17. You ask about not rewriting ports. Not must update checksum since pseudo header includes IP and port. Layering violation, meaning UDP uses field from the IP header. It breaks strict OSI layering. Relates. We talk about layering violations in NAT and Quick. Quick is also a layering violation because it handles transport layer over UDP. 11. If checksum happens to be 0x0000, store as 0xFFFF. Relates. This is the rule of one's complement arithmetic. 12. If checksum error silently discarded, no error message, meaning UDP does not send error messages. It relates. You ask why Quick or TCP need ACKs. UDP is fire and forget, no feedback. 13. Checksums are required RFC 1122. Some vendors disabled to speed up UDP, meaning old systems sometimes cheated, modern system must not. It relates. You ask, is UDP source port 0 normal? No. Many old broken stocks did weird things. Modern systems follow RFCs. 14th, routers have been known to corrupt data. UDP checksums prevents undetectable damage. It relates. You ask about reliability on real internet. Quick encrypts and authenticates. It protects against corruption and tampering far beyond UDP checksum. 15. Given the pseudo header, NOT must modify UDP checksum too, meaning NOT changes IP plus port must adjust checksum. Relates, you asked exactly this earlier. This is why Quick's connection ID helps avoid NOT breakage. Example with SOC and TCP dump. These show real-world ephemeral ports 46274, 46294, UDP fire and forget behavior, ICMP unreachable when destination port close, no retransmissions, no acknowledgements, rates. We discussed ephemeral ports earlier. You ask, how does OS pick a free port? Here you see examples. 17. Linux ephemeral ports ranges can be adjusted via proc/net/ipv4/ip_local_port_range. Relates, you ask how OS selects ephemeral ports. This is exactly where it is configured. IPv6 pseudo header shown in figure 10.4 relates IPv6 requires UDP checksum. Quick over IPv6 relies on this. Final summary. Connecting to all previous messages. This entire section answers multiple earlier questions you asked. Why do Quick packets sit on UDP? Because UDP checksum is simple, fast, and give Quick's freedom. Why does not break UDP unless checksum updated? Because pseudo header includes IP and port. Why are ephemeral ports necessary? Clients need temporary, unique identifiers, otherwise responses break. How does transport demultiplexing work? Pseudo header includes protocol number equals 17 for UDP. Why Quick ignores UDP reliability? UDP checksum only detects corruption, not loss. Why UDP port 0 appears? Older broken implementations not allowed today. Why do browsers send less than 1200 byte Quick packets? To avoid IP fragmentation, checksum plus fragmentation issues. Many designing data-intensive applications. The big ideas behind reliable, scalable, and maintainable systems. Many applications today are data-intensive as opposed to compute-intensive. Raw CPU power is rarely a limiting factor for these applications. Bigger problems are usually the amount of data, the complexity of data, and the speed at which it is changing. A data-intensive application is typically built from standard building blocks that provide commonly needed functionality. For example, many applications need to store data so that they or another application can find it again later. Databases. Remember the result of an expensive operation to speed up reads. Caches. Allow users to search data by keyword or filter it in various ways. Search indexes. Send a message to another process to be handled asynchronously. Stream processing. Periodically crunch a large amount of accumulated data. Batch processing. If that sounds painfully obvious, that's just because these data systems are such a successful abstraction. We use them all the time without thinking too much. When building an application, most engineers wouldn't dream of writing a new data storage engine from scratch because databases are a perfectly good tool for the job. But reality is not that simple. There are many database systems with different characteristics because different applications have different requirements. There are various approaches to caching, several ways of building search indexes, and so on. When building an application, we still need to figure out which tools and which approaches are the most appropriate for the task at hand. And it can be hard to combine tools when you need to do something that a single tool cannot do alone. This book is a journey through both the principles and the practicalities of data systems and how you can use them to build data-intensive applications. We will explore what different tools have in common, what distinguishes them, and how they achieve their characteristics. In this chapter, we will start by exploring the fundamentals of what we are trying to achieve: reliable, scalable, and maintainable data systems. We'll clarify what those things means, outline some ways of thinking about them, and go over the basics that we will need for later chapters. In the following chapters, we will continue layer by layer, looking at different design decisions that need to be considered when working on a data intensive application. Thinking about data systems. We typically think of databases, queues, caches, etc., as being very different categories of tools. Although a database and a message queue have some superficial similarity, both store data for some time. They have a very different access patterns, which means different performance characteristics, and thus very different implementations. So why should we lump them all together under an umbrella like data systems? Many new tools for data storage and processing have emerged in recent years. They are optimized for a variety of different use cases, and they no longer neatly fit into traditional categories. For example, there are data stores that are also used as message queues, Redis, and there are message queues with database-like durability guarantees, API Kafka. The boundaries between the categories are becoming blurred. Secondly, increasingly many applications now have such demanding or wide-ranging requirements that a single tool can no longer meet all of its data processing and storage needs. Instead, the work is broken down into tasks that can be performed efficiently on a single tool, and those different tools are stitched together using application code. For example, if you have an application managed caching layer using Memcache or similar, or a full text search server such as Elasticsearch or SOLR separate from your main database, it's normally the application code's responsibility to keep those caches and indexes in sync with the main database. Figure 1.1 gives a glimpse of what this may look like. We will go into detail in later chapters. Figure 1.1, one possible architecture for a data system that combines several components. When you combine several tools in order to provide a service, the service interface or application programming interface API usually hides those implementation details from clients. Now you have essentially created a new special purpose data system from smaller general purpose components. Your composite data system may provide certain guarantees, i.e., that the cache will be correctly invalidated or updated on writes so that outside clients see consistent results. You are not you are now not only an application developer but also a data system designer. If you are designing a data system or service, a lot of tricky questions arise. How do you ensure that the data remains correct and complete, even when things go wrong internally? How do you provide consistently good performance to clients, even when parts of your system are degraded? How do you scale to handle an increase in load? What does a good API for the service look like? There are many factors that may influence the design of a data system, including the skills and experience of the people involved, legacy system dependencies, the time scale for delivery, your organization's tolerance of different kinds of risk, regulatory constraints, etc. Those factors depend very much on the situation. In this book, we focus on three concerns that are important in most software systems. Reliability. The system should continue to work correctly, performing the correct function at the desired level of performance even in the face of adversity, hardware or software faults, and even human error. See reliability. Scalability. As the system grows in data volume, traffic volume, or complexity, there should be reasonable ways of dealing with that growth. See scalability. Maintainability. Over time, many different people will work on the system, engineering, and operations, both maintaining current behavior and adapting the system to new use cases, and they should all be able to work on it productively. See maintainability. These words are often cast around without a clear understanding of what they mean. In the interest of thoughtful engineering, we will spend the rest of this chapter exploring ways of thinking about reliability, scalability, and maintainability. Then, in the following chapters, we will look at various techniques, architectures, and algorithms that are used in order to achieve those goals. Reliability. Everybody has an intuitive idea of what it means for something to be reliable or unreliable. For software, typical expectations include the application performs the function that the user expected. It can tolerate the user making mistakes or using the software in unexpected ways. Its performance is good enough for the required use case under the expected load and data volume. The system prevents any unauthorized access and abuse. If all those things together mean working correctly, then we can understand reliability as a meaning, roughly, continuing to work correctly even when things go wrong. The things that can go wrong are called faults, and systems that anticipate faults and can cope with them are called fault tolerant or resilient. The former term is slightly misleading. It suggests that we could make a system tolerant for every possible kind of fault, which in reality is not feasible. If the entire planet Earth and all servers on it were swallowed by a black hole, tolerance of that fault would require web hosting in space. Good luck getting that budget item approved. So it only makes sense to talk about tolerating certain types of faults. Note that a fault is not the same as failure. A fault is usually defined as one component of the system deviating from its spec, whereas a failure is when the system as a whole stops providing the required service to the user. It is impossible to reduce the probability of a fault to zero. Therefore, it is usually best to design fault tolerance mechanisms that prevent faults from causing failures. In this book, we cover several techniques for building reliable systems from unreliable parts. Counterintuitively, in such fault-tolerant systems, it can make sense to increase the rate of faults by triggering them deliberately. For example, by randomly killing individual processes without warning. Many critical bugs are actually due to poor error handling. By deliberately inducing faults, you ensure that the fault tolerance machinery is continually exercised and tested, which can increase your confidence that faults will be handled correctly when they occur naturally. The Netflix Chaos Monkey is an example of this approach. Although we generally prefer tolerating faults over preventing faults, there are cases where prevention is better than cure, i.e., because no cure exists. This is the case with security matters. For example, if an attacker has compromised a system and gained access to sensitive data, that event cannot be undone. However, this book mostly deals with the kinds of faults that can be cured, as described in the following sections. Hardware faults. When we think of causes of system failure, hardware faults quickly come to mind. Hard disk crash, RAM becomes faulty, the power grid has a blackout, someone unplugs the wrong network cable. Anyone who has worked with large data centers can tell you that these things happen all the time when you have a lot of machines. Hard disks are reported as having a mean time of failure (MTTF) of about 10 to 50 years. Thus, on a storage cluster with 10,000 disks, we should expect on average one disk to die per day. Our first response is usually to add redundancy to the individual hardware components in order to reduce the failure rate of the system. These may be set up in arrayed configurations. Server may have dual power supplies and hot swappable CPUs, and data centers may have batteries and diesel generators for backup power. When one component dies, the redundant component can take its place while the broken component is replaced. This approach cannot completely prevent hardware problems from causing failures, but it is well understood and can often keep a machine running uninterrupted for years. Until recently, redundancy of hardware components was sufficient for most applications, since it makes total failure of a single machine fairly rare. As long as you can restore a backup onto a new machine fairly quickly, the downtime in case of failure is not catastrophic in most applications. Thus, multi-machine redundancy was only required by a small number of applications for which high availability was absolutely essential. However, as data volumes and applications computing demands have increased, more applications have begun using large number of machines, which proportionally increases the rate of hardware faults. Moreover, in some cloud platforms such as Amazon Web Services, it is fairly common for virtual machine instances to become unavailable without warning, as the platforms are designed to prioritize flexibility and elasticity over single machine reliability. Hence, there is a move toward systems that can tolerate the loss of entire machines by using software fault tolerance techniques in preference or in addition to hardware redundancy. Such systems also have operational advantages. A single server system requires planned downtime. If you need to reboot the machine to apply the operating system security patches, for example, whereas a system that can tolerate machine failure can be patched one node at a time without downtime of the entire system, called a rolling upgrade. See Chapter 4. Software errors. We usually think of hardware faults as being random and independent from each other. One machine's disk failing does not imply that another machine's disk is going to fail. There may be weak correlations, for example due to a common cause, such as the temperature in the server. But otherwise, it is unlikely that a large number of hardware components will fail at the same time. Another class of fault is systematic error within the system. Such faults are harder to anticipate, and because they are correlated across nodes, they tend to cause many more system failures than uncorrelated hardware faults. Examples include a software bug that causes the entire instance of an application server to crash. When given particular bad input, for example, consider the leap second on June 30, 2012 that causes many applications to hang simultaneously due to a bug in Linux kernel. A runaway process that uses up some shared resource, CPU time, memory, disk space, or network bandwidth. A server or a service that the system depends on that slows down, become unresponsive, or start returning corrupted responses. Cascading failures, where a small fault in one component triggers a fault in another component, which in turn triggers further faults. The bugs that cause these kinds of software faults often lie dormant for a long time until they are triggered by an unusual set of circumstances. In those circumstances, it is revealed that the software is making some kind of assumption about its environment, and while that assumption is usually true, it eventually stops being true for some reason. There is no quick solution to the problem of systemic faults in software. Lots of small things can help: carefully thinking about assumptions and interactions in the system, thorough testing, process isolation, allowing processes to crash and restart, measuring, monitoring, and analyzing system behavior in production. If a system is expected to provide some guarantee, for example in a message queue, that the number of incoming messages equal that number of outgoing messages, It can constantly check itself while it's running and raise an alert if a discrepancy is found. Human errors. Human design and build software systems, and the operators who keep the systems running are also human. Even when they have the best intentions, humans are known to be unreliable. For example, one study of large internet services found that configuration errors by operators were the leading cause of outages, whereas hardware faults, servers, or network played a role in only 10 to 25% of outages. How do we make our system reliable in spite of unreliable humans? The best systems combine several approaches. Design systems in a way that minimizes opportunities for error. For example, well-designed abstractions, APIs, and admin interface make it easy to do the right thing and discourage the wrong thing. However, if the interface are too restrictive, people will work around them, negating their benefit, so this is a tricky balance to get right. Decouple the places where people make the most mistakes from the places where they can cause failures. In particular, provide fully featured non-production sandbox environments where people can explore and experiment safely using real data without affecting real users. Test thoroughly at all levels, from unit test to full system integration test and manual test. Automated testing is widely used, well understood, and especially valuable for covering corner cases that rarely arise in normal operation. Allow quick and easy recovery from human errors to minimize the impact in the case of a failure. For example, make it fast to roll back configuration changes, roll out new code gradually so that any unexpected bugs affect only a small subset of users, and provide tools to recompute data in case it turns out that the old computation was incorrect. Set up detailed and clear monitoring, such as performance metrics and error rates. In other engineering disciplines, this is referred to as telemetry. Once a rocket has left the ground, telemetry is essential for tracking what is happening and for understanding failures. Monitoring can show us early warning signals and allow us to check whether any assumptions or constraints are being violated. When a problem occurs, metrics can be invaluable in diagnosing the issue. Implement good management practices and training, a complex and important aspect beyond the scope of this book. How important is reliability? Reliability is not just for nuclear power stations and air traffic control software. More mundane applications are also expected to work reliably. Bugs in business applications cause lost productivity and legal risk if figures are reported incorrectly, and outages of e-commerce sites can have huge cost in terms of lost revenue and damage to reputation. Even non-critical applications, we have a responsibility to our users. Consider a parent who stores all their pictures and videos of their children in your photo application. How would they feel if that database was suddenly corrupted? Would they know how to restore it from a backup? There are situations in which we may choose to sacrifice reliability in order to reduce development cost, i.e., when developing a prototype product for an unproven market, or operational cost for a service with a very narrow profit margin. But we should be very conscious of when we are cutting corners. Scalability. Even if a system is working reliably today, that doesn't mean it will necessarily work reliably in the future. One common reason for degradation is increased load. Perhaps the system has grown from 10,000 concurrent users to 100,000 concurrent users, or from 1 million to 10 million. Perhaps it is processing much larger volumes of data than it did before. Scalability is the term we use to describe a system's ability to cope with increased load. Note, however, that it is not a one-dimensional label that we can attach to a system. It is meaningless to say X is scalable or Y doesn't scale. Rather, discussing scalability means considering questions like, if the system grows in a particular way, what are our options for coping with the growth? And how can we add computing resources to handle the additional load? Describing load. First, we need to succinctly describe the current load on the systems. Only then we can discuss growth questions. What happens if our load doubles? Load can be described with a few numbers, which we call load parameters. The best choice of parameters depend on the architecture of your system. It may be requests per second to a web server, the ratio of reads to writes in a database, the number of simultaneous active users in a chat room, the hit rate on a cache, or something else. Perhaps the average case is what matters for you, or perhaps your bottleneck is dominated by a small number of extreme cases. To make this idea more concrete, let's consider Twitter as an example. Using data published in November 2012, two of Twitter's main operations are post tweet. A user can establish a new message to their followers for 4.6k requests per second on average, over 12k requests per second at peak. Home timeline. A user can view tweets posted by the people they follow, 300k requests per second. Simply handling 12k writes per second, the peak rate for posting tweets, would be fairly easy. However, Twitter's scaling challenge is not primarily due to tweet volume, but due to fan out. Each user follows many people, and each user is followed by many people. There are broadly two ways of implementing these two operations. First, posting a tweet simply inserts the new tweet into a global collection of tweets. When a user requests their home timeline, look up all the people they follow, find all the tweets for each of those users, and merge them, sorted by time. In a relational database like in Figure 1.2, you could write a query such as select tweets, comma users from tweets, next line join users on tweets.sender underscore id equal users.id, next line join follows on follows.follow, followee underscore id equal users.id, next line where follows that follow underscore id equal current underscore user. Second, maintain a cache for each user's home timeline like a mailbox of tweets for each recipient user, see figure 1.3. When a user posts a tweet, look up all the people who follow that user and insert the new tweet into each of their home timeline caches. The request to read the home timeline is then cheap because its result has been computed ahead of time. Figure 1.3, Twitter's data pipeline for delivering tweets to followers with load parameters as of November 2012. The first version of Twitter used Approach 1, but the system struggled to keep up with the load of home timeline queries, so the company switched to Approach 2. This works better because the average rate of published tweets is almost 2 orders of magnitudes lower than the rate of home timeline reads, and so in this case it's preferable to do more work at write time and less at read time. However, the downside of Approach 2 is that posting a tweet now requires a lot of extra work. On average, a tweet is delivered to about 75 followers, so 4.6k tweets per second becomes 345k writes per second to the home timeline caches. But this average hides the fact that the number of followers per user varies widely, and some users have over 30 million followers. This means that a single tweet may result in over 30 million writes to home timelines. Doing this in a timely manner, Twitter tries to deliver tweets to followers within 5 seconds, is a significant challenge. In the example of Twitter, the distribution of followers per user may be weighted by how often those users tweet is a key load parameter for discussing scalability, since it determines the fan out load. Your application may have different characteristics, but you can apply similar principles to reasoning about its load. The final twist of the Twitter anecdote, now that Approach 2 is robustly implemented, Twitter is moving to a hybrid of both approaches. Most users' tweets continue to be fanned out to home timelines, at the time when they are posted, but a small number of users with a very large number of followers, i.e. celebrities, are expected from this fan out. Tweets from any celebrities that a user may follow are fetched separately and merged with that user's home timeline when it's read, like in approach 1. This hybrid approach is able to deliver consistently good performance. We will revisit this example in chapter 12 after we have covered some more technical ground. Describing performance. Once you have described the load on your system, you can investigate what happens when the load increases. You can look at it in two ways. When you increase a load parameter and keep the system resources, CPU, memory, network bandwidth, etc., unchanged, how is the performance of your system affected? When you increase load parameter, how much do you need to increase the resources if you want to keep performance unchanged? Both questions require performance numbers, so let's look briefly at describing the performance of a system. In a batch processing system such as Hadoop, we usually care about throughput, the number of records we can process per second, or the total time it takes to run a job on a dataset of a certain size. In online systems, what's usually more important is the service response time, that is the time between a client sending a request and receiving a response. Latency and response time. Latency and response time are often used synonymously, but they are not the same. The response time is what the client sees, besides the actual time to process the request. The service time. It includes network delays and queuing delays. Latency is the duration that a request is waiting to be handled, during which it is latent, awaiting service. Even if you only make the same request over and over again, you'll get a slightly different response time on every try. In practice, in a system handling a variety of requests, the response time can vary a lot. We therefore need to think of response time not as a single number but as a distribution of values that you can measure. In figure 1.4, each gray bar represents a request to a service and its height shows how long that request took. Most requests are reasonably fast, but there are occasional outliers that take much longer. Perhaps the slow requests are intrinsically more expensive, i.e. because they process more data. But even in a scenario where you'd think all requests should take the same time, you get variation. Random additional latency could be introduced by a context switch to a background process, the loss of a network packet, and TCP retransmission, a garbage collection, pause, a page fault forcing a read from disk, mechanical vibrations in the server rack, or many other causes. Figure 1.4 illustrating mean and percentiles response time for a sample of 100 requests to a service. It's common to see the average response time of a service reported. Strictly speaking, the term average doesn't refer to any particular formula, but in practice it is usually understood as the arithmetic mean. Given n values, add up all the values and divide by n. However, the mean is not a very good metric if you want to know your typical response time, because it doesn't tell you how many users actually experience that delay. Usually it is better to use percentiles. If you take a list of response times and sort it from fastest to slowest, then the median is the halfway point. For example, if your median response time is 200 ms, that means half your request return is less than 200 ms and half your request take longer than that.